Bismillahirrahmanirrahim. Assalamu alaikum. Today we are going to start with lecture number 15, and the topic that we will discuss during this lecture is stack related instructions. We will discuss what the main contents of this lecture. However, before that one, we will discuss what we did in lecture number 14. So in lecture number 14, as you recall, that we discuss about the instruction execution in assembly language and also the main concepts related to the instruction execution. The topics that we discussed, like instruction fetch, instruction decode, and the fetch operands, and execute and write back. So there were different steps to execute a complete instruction. So along with this one, we also discuss about the program counter, instruction register, instruction pointer, and so on, all these registers which are involved during this whole process. After that, we discuss about the conditional flow instructions and the unconditional flow instructions, or we can call them control instructions. Those two instructions include like jump and loop instruction. During jump instruction, we discuss that how we can transfer control to any point inside the code or the code segment. So what we did here, we define label, and after this label, this was a label name, and there were instructions here, and simply we call jump and the label. So this jump and label, so at this label, program transfers its control without any condition. So that was about the jump instruction. And then we also discuss about the loop instruction. This is the conditional control transfer instruction. The syntax is almost similar. So there was label, and we got the program code, and here we use loop and label. However, during this loop, we have the register which has been used as a counter was ECX register. This ECX register was assigned some value, and then we just call loop instruction, and loop instruction automatically decrement. And there was one condition that should match. That condition was that if ECX is not equal to 0, then loop. When if ECX is equal to 0, then the same flow or the sequential flow of the program will continue. And then we also did some example like summing an array, integer array. So how we can sum up all these array by using this loop instruction and so on. And that was one example that we did. And also by using these loop instructions, and also previous lectures. So during this lecture, the topics that we will discuss in this lecture number 15 include runtime stack, the concept of stacks, how we can use a stack, what is the concept of a stack, how stacks are maintained inside the memory, what are the operations inside these stacks. And there are a few instructions which we will use. One is the push operation, and the second one is called the pop operation. And there are some variants of these instructions like push AD, pop AD, push A, pop A, and so on. So we will use all those. We will discuss all those instructions during this lecture. Now, before going to start discussing all these instructions, first we will see what is a stack. So here you can see a stack. Just imagine there is a stack of plate. For example, here the entry point is only this one. This is the only entry point is called the top, and this point is called the bottom. So we are going to add plates. For example, plate number 1, plate number first initially we add plate number 1, then plate number 2, and so on, and up to plate number 10, and so on. So only there is a wall or boundary, so we can add these plates inside this stack or on this stack. So all these plates can be added or removed, can be inserted or added inside this stack from the top and removed from the top only. So how we can do that one? For example, if we add plate number 1, then we can add plate number 2 and 3 and so on up to, for example, we added 10 plates, and the first plate that we added was plate number 1, and the last plate that we added inside this stack is plate number 10. Now this was the addition process. This process is called to push, means we push items or some elements inside the stack or operands inside the stack. Now the second operation is to remove or to pop. So to remove from this stack, the last plate that we added is a plate number 10. So it's not possible, you cannot remove this plate number 9 or 8. So this is the plate which you will remove first. So that is the reason the last plate was 10 when we added all these 10 plates, and the first plate that we will remove will be the plate number 10. So that is the reason this stack structure or stack data structure is called the LIFO structure. So in this LIFO structure, LIFO, what is LIFO? LIFO is last in, first out. So this plate number 10 was lost, that we inserted or added inside the stack. That is the first instruction, first plate that will be removed. Now there are two concepts. One is the bottom, or the pointer which shows the bottom. Second one is called the top. So this top pointer, first of all, for example, when we add plate number 1, so top will be here. When we add plate number 2, so top will point here. 3, 4 and 5, and top will point to this last plate that we added. So this is a pointer which keeps the track, how many plates are, what is the last plate that we have added and what is its location. Now this is general example. You can have any other example like the stack of towels or something whatsoever. So the concept is similar. However, in general life, we can remove plates from the inside or from the middle or from anywhere, not from top and bottom. But here the concept is we can remove from the top only. So you can imagine any example. This is very basic discussion about stacks. If you have the course related to data structures, then you will learn this data structure in more detail about the stacks. So how these stacks are being maintained inside the memory. Now we know that memory has some starting point. For example, memory start from addresses 00000 and up to FF and so on, 0x and 0x to show them in hexadecimal. So this is the growing direction of the memory. Okay. Now similarly, we can have another representation of memory, that our memory starts from here 0000 and so on, and the last location is FF and so on. So in this way, the growing direction of memory is this one. So either memory can grow upward or downward, it doesn't matter. But now we will discuss how stacks are being maintained inside the memory. Now for example, consider that memory grows in this direction. So here the direction that memory grows is downward direction. So the 00 should be somewhere here, 00 hexadecimal should be somewhere here, and FF should be at this point and so on. So all these addresses and all these addresses here. This is complete memory diagram. Now how a stack grows, to show the convention that stack grows upward, for example, then we have used this notation that memory grows in downward direction, for example, then the stack grows in upward direction like this one. So here you can see the stack grows in this way. If we add elements will be added like this one, and we will decrement the addresses. For example, address is 1000, and then if we decrement, then how many elements or how many bytes we decrement to add another element. We will discuss in the later point, but here So there are two registers. Which registers are being involved to manage all those stacks? There are two registers. First register is stack segment. This shows the starting point, and then we have the stack pointer. A stack pointer is in the real addressing mode, we use a stack pointer to manage all those stacks. In the flat or in other architectures, we do not use segment registers and so on, but we can use this stack segment register. In contrast or in combination with the stack segment and ESP or stack pointer, these two registers, like ESP works as an offset and segment register works as an a starting point. So offset and a starting point, as we know that when we add these two, then we can form the effective address. The effective address will be segment register and plus the stack pointer. So when we add these two, then we can locate our stack. So a stack segment is the register which shows the starting point, and the stack pointer shows the last location of the last element that we have added. Okay, here you can see there is, for example, there is only one element which has been added here. So a stack pointer shows the location like 0 0 0 1 0 0. Now this element or the operand or value is 4-byte value. Sorry. So this is the 4-byte value that we have added inside the stack. And now you can see that it occupies 4 bytes starting from, this is the, I just write here, this is the 4-byte value. This value can be value or the value inside the register, or direct value, or the immediate value, or direct constant, or it can be value inside the memory location somewhere else like variable and something. So we have added one first element. Here you can see ESP points this location, and the next point is 1 0 0 minus 4. So it should be like, so if it is 1 0 0 and 0, next location should be FF F FFE and FFD. So these are the 4 memory locations, or 4 consecutive memory locations that store 4-byte information or value. They can grow like in this direction, it's okay, no problem. So here they can grow in 0 0 0 and 1 0 0 and hexadecimal. Then here should be F F F and so on, then F F F E and F F D. So all these 4 bytes are being occupied by one value. So we have pushed one value or one 4-byte value inside the stack. Now what will happen, what are the operations like push and pop? When we perform push and when we perform pop operation, what will happen inside this stack? So here you can see a push operation. When we push, for example, a 32-bit push operation is shown here, or 4-byte. This is 4-byte value that we push inside this stack. So before performing this push operation, first it decrements the stack pointer. First is decrement the stack pointer by 4, because we are going to store 4 bytes, and copies of value into the location pointed by the stack pointer. For example, initially stack pointer was here at this point, and some value, 4-byte value, was stored between these 4 bytes from 1 0 0 to FFD. And now what we are going to do, we are going to add another element or another value. That value is for example A5, and this is for example 0 0 0, all zeros, and A5, all these 8 digits, hexadecimal digits, we want to add inside the stack. So before going to add this one, we will decrement a stack pointer, or it will automatically be decremented based on the number of bytes or size of the value that we are going to push inside the stack. So when we push 32-bit any value, then it will decrement 4 bytes from the address, and it will store this value at the new location which is being pointed by the this stack pointer register. So this is the push operation. Now what will happen when we push this value? Next operation is, if we push another value, for example, if we want to push another 32-bit value, what will happen? So if we push another one, for example, then stack pointer will automatically decrement it 4 bytes. So stack pointer was previously pointing to FFC, and after FFC, for example, FFC, then FFB, A, and then 0. So FFC, B, A, and 0. So sorry, it should be 9 here, not 0 but 9. So FF9 and so on. So this is the value that we are going to store here, for example, inside this one, 9, A, B, C, and so on. So this value has already occupied these 4 memory locations. Now we are going to decrement 4, and then the new location should be FF8. So at this FF8, new element will be stored. So this is you are going to add new values, 32-bit values or 4-byte values. Then stack pointer is decremented by 4, and new value will be added. Now here, if we add another element, this will happen like this one. So same mistake when we push 2 more times. So the area inside the direction of the ESP grows. Here you can see. So this is the growing direction for the stack, and actually this is direction for the memory, in which direction memory grows. So the area and the direction of ESP grows is always available, and unless the stack has been overflowed. For example, a stack has some number of bytes allocated, that this area should be used as a stack. If this growing direction exceeds those number of bytes, then it will give us the stack overflow error in case if we exceed that limit. So this was the push operation. Now just remember one thing: if we push before going to push any value, it will decrement the number of bytes or size of the operand that or value that we push inside the stack. Then it will add the element at that location. Now the next one is the pop operation. What will happen here, if we this is the stack pointer right now, what will happen? So this copies the value in the our variable, and it's the stack pointer where n is the either 2 or 4. This pop operation, value of n depends on the attribute of the operand and the receiving data whatsoever. Now before, this was the show the image of the stack. There were like 1, 2, 3, 4, and 4 elements inside this stack. Now if we want to perform pop operation is totally reverse in a sense that in push operation, first we decrement, then we add element. Now pop operation is totally opposite. First we read, for example, first we read this value and assign somewhere else to register or some memory location or some variable, and then we increment that how much data we are going to read from this stack, and then we increment. So here, in case if we increment, if we read 32 bits or 4-byte data, then this stack pointer will be incremented by 4. So this is the new location or the top of the stack, the last element that we can. This was the last element, but after pop, this is the last element that we can read from the stack. So this is the pop operation. Now the syntax of this push and pop. Now I will repeat again that for push, first we decrement the number of bytes, for example either 2-byte or like word or the byte or maybe double word and so on. So it will be pushed inside the stack, but before going to push, we decrement from the stack pointer, then we add that value to that location. For the pop operation, first we will read the value from that location, and then we increment the number of bytes of which the size of the operand that we read. Here you can see we have multiple instructions or multiple formats or syntax for push and pop. First one is we can have push R or M16. We can push any register value or memory of 16 bits. We can push and pop register or variable of 32 bits, and we can have immediate value for 32 and 16 bit and so on. Here you can see all these push operations that you can perform inside assembly, and also we have the pop operation. Now there is one difference in the pop. When we push, we can push either register value or variable or memory location and so on, or third one is a constant. Keep in mind, constant. So whatsoever the value is either in register, either inside the variable or in any constant. But as far as the pop is concerned, what we can do when we pop, and here we define something where the value will be read from the stack and assigned to this variable or to this register. We cannot define constant here. We cannot use any constant here because we are going to read some data from the stack and assign to some memory location or assign to some register. So that is the difference. Constant is a value, or it doesn't hold any memory location. So we can either assign or pop any data from stack and move towards the register or towards any variable or any memory location. However, we cannot use any constant, but inside push you can push contents from memory location or from register or either a constant value. So just keep this point in your mind. Now using push and pop operation, for example, when we perform push operation and when we perform pop operation, you know that the sequence, when we push first element, second element and third element, the pop operation should be in reverse order. For example, we can save and restore registers when they contain some important values. For example, in case we use the loop instruction, multiple loops, there was inner loop and there was outer loop in our previous lecture. So what was the problem? That we defined some the variables that temporarily hold the value of ECX to hold the value of this counter for the outer loop, and then we started inner loop by assigning a new value to the ECX, because this same ECX was used for two loops, outer loop and inner loop. When we move from outer loop to inner loop, we just save the contents of ECX. So instead of defining multiple variables, if we have 4 or 5 inner loops, then we have to define 4 or 5 memory locations or variables that hold the ECX value of ECX to keep track how we can go back for the outer loops. Similarly, sometimes when in future we will use the procedures, as you know that procedures are, we call procedures, we define, we call procedures, and we return from the procedure to the main program and so on. So before moving to the procedure, so these procedures perform some operations on registers like accumulator or AX register, EX register or whatsoever, EBX, ECX and so on. All these registers are being used inside the procedure, and when we call a procedure, before that one we save most of the registers which hold the important information. When we return from the procedure, what we do, we just pop all those, restore all those registers. So during those procedures or these calls, we also use push and pop. This is very handy. We can temporarily store somewhere all the important values, and then we call them or we read them. Here is one example. So this is more important, just the opposite order. For example, if we push and if we pop. These push and pop instruction, they occur in the opposite order. For example, first we push ESI, ECX and EBX, 3 registers. For example, this is the stack. First in register or the contents of register that we push is ESI. The next register contents are ECX. The third register is the EBX. Okay, so these are the 3 push operations. Now what we do, we do some manipulation and so on to all those registers and whatsoever. Now we need the original values before these operations, from here to here. Whatsoever we did on those registers, we are not concerned. We perform the execution and so on. Now we need the original values before this point number 1, and we are here at point number 2. So when we come to point number 2, we need all the values of these registers, ESI, ECX and EBX, when we pass this point number 2. So you can assume this is a complete loop, or this can be a procedure, or this can be anything whatsoever you can call it, whatsoever you can imagine right now. So what will happen, we have to pop those values. Now you can see the top element is EBX. So first we can only retrieve, or we can pop the value of EBX. So first is the EBX that we popped, then the next value that we can pop is the ECX, and the third value is the ESI. The order is the reverse order. First EBX, then ECX, then the third one is ESI. So this is the order which you can reverse. Now how can we, in case of nested loops, for example, how we can do all this in nested loops? For example, inside the nested loop we have to we wanted to execute this outer loop 100 times, for example, 100 times, and from here there's inner loop. So this ECX value is for the outer loop, this ECX is used as a counter for the inner loop. So when we move from here to the nested loop or an inner loop, what we will do first we will store or push the value of ECX, then we will perform. So ECX value, for example, initially is 199 or something whatsoever, or the 100 value or 99 whatsoever you can call it. So this current value is, for example, 100, that has been pushed. Now this is the new value for ECX. So inner loop will manipulate all these values, or this ECX as a counter. It will decrement during each iteration when the loop will repeat itself. Then what will happen when the loop exits? The first instruction that we want to do is to pop ECX, pop the original value or the previous value before starting this loop number 2 or inner loop. So we pop that one. So this is one example that we will use here. Now we want to do all these this inside the, and there are some other instructions, related instruction that we will use for the stacks. Those instructions include push FD and pop FD. Then next one is push AD and pop AD, and there are some variants. What is the purpose of all these instructions? For example, you know that flags, we perform some execution inside the program. We have some values inside the registers like EAX, EBX and so on, all these registers. When we perform some operations, we keep the track of the flags. The name of this flag register is, so we have the flag register, or we have flags, or E-flags register, E-flag register. So we want to also store this flag register. How we can store flag register? By using push FD, and we can pop FD is the opposite. We can read all those flags which we have stored inside the stack. Similarly, which we have the next instruction that we have is push AD and pop AD. Push AD is the instruction that stores all these general purpose registers inside the stack, or it pushes or stores or adds the values of all those registers inside the stack. So the order is like EX register will be added first, then ECX, EDX, EBS, ESP, EBP, ESI, and EDI. All these general purpose registers, they will be stored inside the stack. If we say pop AD, it will restore all the registers from the or reads all those registers in the reverse order, so they will get back all their values, original values that we have stored in all these registers. So push AD and pop AD stores all these registers inside the stack, and pop AD reads all those registers inside from the stack and moves towards the registers like EX, EBX, and ECX, so on. Similarly, if we want to store all the 16-bit registers like AX, BX, DX, BX, SP, BP, SI, and DI, these are 16-bit registers. So if you want to store 16-bit registers, you have to use push A and pop A. They have the same purpose that you want to use. Now what we are going to do, we are going to start with the assembly language. So we will create a new project and we will see how we can perform all those actions or all these operations inside the assembly. So we want to save this project like we have lecture number 15. This is the console project. Okay. So first of all, the same build customization, then we have to add a file. We can add new item, any file you can select here. Name is example 001a.asm. okay, and then we have to select the preferences for the macro assembler. Include path should be MASM32, and we have the okay, so it's ready. Now what we can do here, for example, I have few examples. The skeleton of the program, I just copy the skeleton instead of writing complete. So this is complete skeleton. I just save this one. Okay, now here inside the data segment, our data, we are going to say, for example, variable 1 double word, and its data is, for example, 21 in decimal. Variable 2 is double word, 22 in decimal, and so on, for example. Or if you want to have hexadecimal, you can write hexadecimal, and so on. So this is simple program. What we do here, we want to have for example, move AD or EAX, move EAX comma variable 1, and we do push EAX, just simple one instruction, push EX. Then we can see, so we just build the solution. So it's succeeded. We just execute this one. Now here you can see registers. Just look at all those registers here. This is the 00AD, and this is the data section where our variables are being stored. So this value 0000 and 15, it's equivalent to 21 in decimal. So 15 is in hexadecimal. So EAX will be moved. Okay, so EAX is the same value. Now this is the stack pointer. Stack pointer value is pointing to somewhere 034, F8, F0, and so on. Now if I push EAX, you will see that stack pointer will be decremented. Now F0 is here. If I say, so it has been decremented. What was the previous value and what is the new value? So stack pointer shows the location where our values are being stored. Now we have pushed EAX, and now you saw that stack pointer has been decremented. Instead of incrementing, it has been decremented. Previous value was F0, now it is EC. So F0 and now it is EC. So it means 4 bytes have been decremented because this is double word. Okay. Now I want to just, this is push operation, and we can use the same pop operation, or I want to use the another variable. For variable 2 is the word, and its value is 21, for example, or 22. So push EAX, push, for example, if I say push variable 2, then see what will happen here. So it succeeded. Now if I want to use this one, so stack pointer is this is the location for the stack pointer. Now we can go to this location and we look at what are the memory contents. So I just go there. For example, we just start with debug and Windows, then we start with the memory and memory 1. So this is memory 1. A starting point is, for example, for this memory is 000 and 35 FC and 58. Okay, so this is the memory location. So here, from here, this is the stack pointer starts from here. Now if we are going to store anything 4 byte, they will occupy this area. If we want to store some other data, this will occupy the rest of the upper section. So what I want to do, I want to F10, so 15 or that is equivalent to 21 and decimal has been moved to EAX. So first we are going to move the contents of register E, means EAX register. So they have been moved. You can see here they have been moved from here to here, 000 and 15, 000 and 15, because this is little endian system. So 15 has been here, added here, and 000 they are here. Now this is the new location for this stack pointer. That new location is pointing to at this point. The location name is 003F, FC, and 54. So it is pointing here that we have added this whole 4 byte information. If I execute again, then what will happen? So this 2 byte or word information, that is equivalent to 22 in decimal, and its hexadecimal equivalent value is 16. So that has been added to this one. Now this should be the new location where our stack pointer is pointing. It should be 0035 FC and 52. So here you can see 0035 FC and 52. So it means whatsoever we push, our memory grows in this direction, but our stack grows in the opposite direction. So just keep in this in your mind that our stack grows in this upward direction, and memory grows in this downward direction, because 50 is this location, 51, 52, 34, and so on. Our stack started from here. Now this was how stack grows and how data is being stored inside the stack. Now if I want to perform pop operation, it's not necessary that we have first we stored double word, then we have stored word information, and double word was stored by pushing the EAX register, 32-bit register, and word was stored by using some variable, or variable 2 was the name. So we use this variable 2 to store inside the stack. Now we want to perform pop operation, so I just finished this one. Sorry, I just make some modifications. I just remove this one, and I just stop. So here now I want to push, and then I want to pop AX, then pop EAX. So these are the two operations we have to build this project. Successful, and I want to execute this one. Here you can see now this is dynamic memory location, so the new location where this stack starts is this one. I just copy this one here. Sorry. So this is the new location where our stack starts. So you can see all these are 0, 0, and this is complete stack area. So I want to move towards the same starting point, and you can see what will happen. So from here our stack will grow. So first instruction is this is the first instruction, move the contents of variable 1 toward the EAX. So variable 1's contents have been moved to EAX. We have stored this 4-byte information inside the stack. Then we have pushed the contents of this variable 2. Then we are going to perform pop AX. So you can see we performed pop here. These 2 bytes have been read in the AX register, or 16-bit. We know that we have stored 16 bits, so we read 16 bits or word information. Then again we are going to perform pop operation. So we perform pop operation, so we read the same value for this whole register, and then this is end of the program. So it doesn't mean that if you store the contents of register, then it is not necessary that you can read or pop those contents inside the register. Not necessary. Just keep in your mind that the area should be, or the value should be same. For example, if I stored word, double word, then I use double word, for example, restore pop, and double word to read. For the push, double word, and pop, double word. So these are opposite. This is the first we push 32 bits, then we push 16 bits, then after that when we pop then we pop here 32 bits first, then we pop 16 bits. Sorry, I made mistake. So first we pop 16 bits because AX is 16 bits, then we pop 32 bits. Okay, but when we first push 32 bits, we used EAX register 32 bit. Then we used a variable. The size of this variable was 16 bits. Now what happened here, we use variable for 16-bit push operation, and 32-bit we use register. Here what we are going to do, we are going to pop by using AX register. So contents from the stack, 16-bit contents, they will be read inside this AX, and EAX will have the 32-bit contents. So EAX, we have used the same EAX register, and we have we used in the push operation, we use same for the pop operation, but here we have made some changes to clarify the idea. It is not necessary that if you push the contents of register, then you have to read those contents inside the register. Just keep in your mind that size should be same. What will happen if the size is different? What will happen? Now we will take one example, and then you will see what will happen. For example, what I do here, I want to push EAX, then pop variable 2, push variable 2. I push EAX, and then 2 times EAX has been popped. We pushed 32 bits first, then 16 bits. We are going to push pop 32 bits and again 32 bits. What will happen? Just see. We just build this one. Okay. So the memory for this stack pointer is this one. We just go to this location and observe the stack. Here our stack start from here. So first EAX is 15. This 15 has been stored inside this all 4 bytes. Then next one is, and the next one here we restored this 2 bytes. So our total stack occupies these 6 bytes from here to here. Okay. Now what will happen if we perform pop? Now initially we are going to perform 32-bit pop operation. Okay. Just visualize the contents of EAX register. Can you see here? The first value that has been read is these 8 bits and also 8 bits from this pop operation. So all these from here to here, we have read this 32 bits. Systematically or in order to keep the order, we first have to pop 16 bits, not 32 bits. So the value is wrong. The value which we read from the memory is wrong because the value was supposed to be 16 bits and the value should be 16. And if you convert this whole value right now, it is 00150016. It will give you the wrong value in decimal, or if you want to have an hexadecimal whatsoever. Now what will happen if we perform another pop operation, 32 bits? Can you see here? This is another pop operation. So now we are reading some other information from here. 36, all these 4 bytes. 36, 77, 00 and 00. So that has been read, and here. So you can see here that the value that we read or popped is wrong value. The value was supposed to be 000 and 16. So just keep in your mind when you push. Sorry, I just make some changes. I'll just break this one. I want to run it again, and then I'll just stop this one. I just build. So I just build again. So this one updated. Rebuild the solution. Okay, I just execute, and this is the stack pointer. We just go to this stack pointer and see. So stack pointer is this one. It grows from here, and we just run. So first this element has been added, then this element has been added. We perform pop operation for this one. So pop operation performed here, next pop operation, and then so there's a unexpected at this one, 07 A02 F7, because we are violating this area. So we are violating this area, so we have to keep track. We do not need to violate the starting point of the stack, because if we violate the starting point or the stack segment or the area which is being allocated to the stack, then you will get error, because system has already allocated some specific number of bytes or a specific section of memory towards the stack. So keep this in your mind. For example, if I use AX here and 16 bits, and I just save this one and perform this. Okay, so there is no error right now. I have performed all the operations. I will perform again to show you. For example, here the stack pointer, we can just go towards this stack pointer. This was the point I was trying to make here in the end before moving towards the other instructions. So this is a starting point. First instruction F10 for the first instruction we have executed. Now a step over, we push EAX, this value 0, 0, 0 and 15. So this is 15 here, 4 byte. Next should be for this pointer is here, for the F814. Now the pointer, stack pointer is F812. You can see now we are going to pop. We are going to pop in a wrong order. So we are going to pop, instead of 16 bits or 2 bytes, we are going to pop 32 bits. So you can see EAX will be 00150016, and here we are going to pop 16 bits or 2 bytes, so it should be 00. So actually 15 is the previous value inside the AX, so only AX has been updated here. So here you can see, if you finish this execution, you will not get any error, but if you violate the boundaries, starting point and the up to the top, whatsoever the limit has been given to you, stack underflow and stack overflow, if you are going to pop when stack is empty or when stack pointer is at the bottom, so you will get underflow error. If you increase the location or the area which has been allocated to the stack, you will receive the error like stack overflow and stack underflow in these two situations when we are at the bottom. And if you perform pop operation again, you will get this stack overflow and underflow. For example, if I perform here pop EAX, this is, we are at the bottom, this point we will reach toward the bottom, and if I just build this one and I just execute, so this will be the execution time error. So we will monitor this stack here, we just monitor. So now you can see this is the bottom area. When a stack pointer points here, means our stack starts from here. When we perform some push operation, first decrement, then store, and then reverse for the pop operation. Now first I want to push. You can see here, first when I push, so this 00015 will be pushed here. Okay, now stack pointer is pointing to this point, this location. Okay, the starting location is this one. Again, if I push, so 16 has been added here. Now pop operation, this 32 bits will be popped, even though the order is wrong, but we are still not violating this one. So pop operation we popped, and now the instruction, the stack pointer is up to 00A here, 00A, and now I'm going to pop 16 bits. So this 16 bit is still we are not violating. Now this is the first point where we started. This is the bottom of the stack. When stack pointer the bottom starting location and the stack pointer has the same address, it means we are at the bottom of the stack. Now if I perform pop operation, it will perform, but we are still violating. So we have read this value, we have violated. When we perform invoke or another instruction, you will get the error. So we have exited here. It was supposed to be violation. Okay, for example, if we perform EAX here and we save, if we build this project, build solution, so here is the stack. So we just execute. So we pushed all these values. Now we perform pop, and when we execute, perform another pop operation, we violate this area, this stack area. So you will get unhandled exception and so on. So you will get the error. So you can see all this program counter, everything has been modified, and you will get the error. So just try to avoid this situation. So I just stop this one here, and what will happen, so this was about the push and pop. Now we want to do some other instruction like push FD and push pop FD and so on. So for example, here we have the I just remove all this one. push FD is the flag register. So if I say add EX, I just use the double word, and they should be in hexadecimal. Okay, variable 2, save, and I want to push FD and just store, just build. So just execute this one, and I want to show you the flags. So if I use flags, so here you can see all these flags. These are individual flags. So what will happen when I say this is flag register is what is the starting point for this stack pointer? Stack pointer starts from here. So this flag contents will be stored in this at this point here. So execute. So this is first EX is equal to variable 1, then we perform add. So this 0 and this one, these two flags have been modified, and if we want to store all these registers, for example this whole complete register, so you can see this flag register 00, 00, 02, these contents have been stored inside this one. So 02, 02, 02 and all these 00s, they have been stored. So this flag register, E flag register, have been stored inside this whole stack. For example, if I just complete the execution and if I perform other operations like push, or if I just add EX comma, or if I do just subtract EX comma variable 2, subtract EX comma variable 1, and here will be the new value for the flag register, you will see. And after that, if I perform pop FD, then what will happen? So I just build the solution. It's okay. Now we have to monitor this area. Okay, just come to this point here and you can monitor, we execute. So this is the first value inside the EAX variable 1. Now what we are going to do, we are going to perform EAX addition with the whatsoever the value inside the EAX and variable 2. So 21 hexadecimal 22, they will be added. So it is 43 hexadecimal, and these are the flag registers. So this is a flag register. We are going to push this flag register. So flag register has been pushed. Then we are going to perform subtraction. We perform subtraction. Now the flag register is 0, 0, 0, 0, 2, 0, 6 and so on. Now 0 flag is 1 because the value is 0 now. 0 flag is equal to 1. This flag is high. So the new contents of flag register are 0, 0, 0, 2, 4, 6. Now if we perform pop, you can see we have popped the contents of this flag register that we pushed inside the stack. So these flag or this flag information is also important if you want to push flag information or if you want to store flag information somewhere inside the stack. So you can do that one by using this push FD and pop FD. Now once again, this is about the flags. We just close this one, and then one thing that we are going to do right now is to push AD and pop AD. For example, initially can we just assign move EX EX comma 0 0 1 or only 1, move EBX 2, move ECX 3 and move. Then we have the other contents like, okay, these three registers for your convention. We will note their values. Now if I say push AD, so I just built, so it's successful. Now here you can see first the note down the contents for ESI and EDX. Okay, EDX has this value and EX, EBX, ECX and so on. So first we will go to the stack pointer. For example, just come to the stack pointer, even though the stack pointer's value is being stored here. So here is the starting point. So what will happen, first instruction that will be executed is EX is equal 1, EBX is equal 2, ECX is equal 3. Now instruction pointer and all these registers you can see here. If I just push AD, note down EX, EBX, ECX and EDX and all these. So here EX has been, then next one is instruction pointer for the this value is for the ECX, so this is the value which we have been stored. Then we have EDX, these 4 bytes for EDX. From here to here is EDX. Then we have EBX. EBX is 02. Then the third, next one is the contents for the stack pointer, then base pointer, the EBP, and so on. So this is the sequence in which values will be stored inside the stack. Now, for example, I just terminate this one, and I want to perform here some operations. For example, move EX comma 2 or 1 2, move EDX comma 3, and this one is 4, and so on. If I say I want to change these values, I want to change their values. For example, I have changed the values for all these registers like this one. So here you can see I want to move their values like 1 2 2 2 2 3 2 and 4 2, for example. And after that, after changing, if I want to know what were the previous values, and pop AD. Okay, so can we get the previous values 1 2 3 4 and whatsoever we stored inside these registers? Here we just build this solution, and then you can see here I just execute. We have to monitor this stack. Sorry, this should be this value without a space. Okay, so we want to change the, so first instruction, change the contents of the A register, accumulator B, C, and just DX and then CX. Okay, so 1 2 3 and 4, whatsoever these contents for AX, BX, DX and CX. Now we want to push their values inside the stack. So you can see stack has been modified. All these values have been modified inside the stack. Now we want to change the contents for these registers. So AX, BX, CX, they have been changed, and we want to pop. So you can see we have popped the values for the all these 00, 01, 02, 03 for EDX, and 04 for this one ECX. And for the ESI and EDI, their contents were 0, and now even though after pop operation their contents are again 0, and so on. So there is no change in those registers. Otherwise they have been also popped from this stack. Now this was all about the this example. Now we have performed this push and pop operation, and push A, pop A, push AD and pop AD. Now before performing this, all this one, if I say push A and pop A. So this is another instruction, but what will happen, this instruction will 16-bit contents, they will be moved toward the stack or inside the stack. I just build, and so these contents, the stack pointer is from here. So only these, first of all, I will just run 1, 2, 3, 4. So these 16-bit values, they will be moved inside the stack. Here you can see only 16-bit values. So you can see, so this one and all these values have been moved, push A and pop A, and then again if I just recall those values, so they have been read. So we have read, so actually it is going to read those EX and so on. So push and pop A has the same effect on this one. So I just terminate this one. Now what I will do here, I will open the previous example. Previous example we did the inner loop and outer loop, and we performed some operations. So I just open, I just remove this one, I just remove this file, and I just add the previous existing item. So no, add the existing item, and the item was lecture number 15. I just go inside the lecture number 15. So here is the example number. So this is the empty project, I think. Okay. This is empty one. So okay. Okay, so this is example that we did in our previous lecture. The example was about how we can perform. So 3 times we perform the outer loop, and then we perform some operation like move EX by 4 and so on. Then we save the counter, and then we have another one. So we have another one here. So we have to, this is the outer loop, and we save this counter for ECX. We assign new value for the ECX. We decrement EX and so on. So actually we want to do this one, like first we assign 4 to EX, then we decrement it 4 times, it becomes 0 inside the inner loop, and then again come back. So we assign 4 to the AX register in the outer loop, and inside the inner loop we decrement 4 times to EX to make it 0, and again we continue the loop. So this continuous, this will continue for 3 times, and for all these 3 times we just remove or decrement the EX and assign again the value 4. Okay, so here what we do, we use one variable, and the name of this variable was counter1. So first I just run this one, just, and then show you what's going to happen here. If the solution is perfect, so successful, I just run this one. Here you can see the initially, so ECX is equal 3. Now we move 4 towards the EX, so ECX has been moved towards the counter, so it's okay. Now ECX has a new value, and now it will continue the loop 3 or 4 times, and now it will decrement the contents 3 times, first time, second time, and now this is 3rd time, and after that it will exit. Now we are using counter here as a temporary register or temporary storage to hold this value. Now if we have multiple registers, then how we can add or store all those registers inside the temporary store their values, and after some time we want to retrieve their values. So instead of doing this one, what we do, we make some modification here. The modification is push ECX. Okay, so what it will do, so it will save outer loop or LP1 counter and retrieve the LP1 counter. Here at the this one we use, so here is the pop, okay, pop ECX. So this is very convenient. We don't need to keep track of all those defining new variables. So instead of using these different variables and keep track of all those variables, we just add or push all those registers or their variables or values of those registers or values of the memory locations or these variables. So we just push and pop. Very simple. I just run this program and you will see here. So build is successful. So build is successful. Now I just run this program. Just minimize this one. So here you can see we have this, and stack pointer is this stack pointer, and I want to monitor this memory area. So memory is in debug Windows, and inside Windows there is memory and then memory 1. So if you want to have multiple memories, and you can have multiple memories to monitor. Here I want to execute first instruction ECX is equal 3, ECX is equal 3, then move EX is equal 4, so EX is equal 4. Now I want to push ECX, so this whole word double word or all the contents of ECX has been pushed, 32 bits have been pushed. Now again what we are going to do, we are going to decrement this one or assign new value to ECX. You can see here we have assigned new value to ECX, but however the previous contents of ECX have been stored in here. Now it will decrement, every loop will decrement, so ECX it is 0. Now it is as exit from this loop, and now we are going to pop ECX. So ECX value was 03, it will be popped inside the ECX. Now when we will continue from loop 1 or when we execute loop instruction, it will decrement inside the ECX. So now the new value for ECX, when we moved here, previously it was 03, now we are not going to move here or going to jump here one instruction after this one. So the new value for ECX is equal to 02. What we are going to do, we are going to EX is again assigned 4, and now the new value of ECX is equal to 02. We want to push, so it has been pushed here because we popped. A stack pointer was here. When we pushed, again the stack pointer will be here. So the operation, we are decrementing second time the contents of ECX register, and now we pop ECX, so ECX is equal to 2, and we check the condition. Now the new value for ECX is equal to 1. We push this 1 value here and continue this all decrement operation, and when we come here pop, so this value will come here in the ECX, and when we'll check the condition, ECX was decremented, it was equal to 0, and then it will exit from this loop and so on. So this is the way when we use multiple loops or nested loops. So you can use push and pop as accordingly. So this was the discussion about the push pop, push AD, pop AD, push FD, and pop FD, and so on. So now we will summarize. We discuss that about the runtime stack, that how a stack is going to be maintained inside the memory and so on. And we also discuss about the push operation, This push operation determines it decrements first n bytes from the ESP and then store n bytes. So it can store or add either register contents, either memory contents, either immediate value, and so on. But it determines what is the size of the register, what is the size of this memory address or variable. So accordingly it decrements. But first it decrements and then adds. Pop operation is reverse. So a stack pointer, first we will read from the stack pointer, then we increment. So the direction is opposite. Memory, if a memory is increasing in this direction, a stack will grow in this other opposite direction. Okay, and then we also saw some push instructions and so on. Their variants were like push AD, pop AD, and so on, and the related instructions. And then we also saw how we can use push FD, pop FD, push AD, pop AD, and push A and pop, and so on. And this is end of the lecture. Hope to see you in the next lecture, inshallah. Till then, Allah Hafiz.